Okay, so good evening, everyone. So before I start, anyone with any questions? Okay, so seems like not. Some of you contacted me about PTE numbers today. I haven't gotten around to it, but I'll be handing them out to everyone. Um, uh, I think some of those of you who contacted before today, I think I already responded to three or four of them. So anyway, everyone will get a PTE who needs one. Okay, so today's lecture, we are going to continue on the theme of some of the hardware related issues, and then I'll move on to software organization, which is the third slide set, and it is on Piazza as well. So towards the very end, we were talking about what kind of metrics sort of one needs to look at when considering embedded platforms, and also how there is kind of a fair bit of range that exists between the class of devices that normally we think of embedded platforms, and we had talked about some of these things. Okay, so uh, the specific platform, just to give you a sense, so that we are using in this course is this Arduino Nano 33BLE Sense. So Nano is just because it's among the tiniest of the Arduino devices. 33 is because, unlike the older Arduino devices which were operating at 5-volt IO, this one operates at 3.3 volts. BLE is Bluetooth low energy, and Sense is because it has a whole bunch of sensors on board. But importantly for us, and the reason I picked this one is because of the processor it uses. This module that you see on which says blocks, BLOX, this is a module which uses a process. Internally, it uses a processor from a company called Nordic RF, which makes some pretty cool embedded processors around ARM. In this particular case, a processor called 52840, and it is together with a Bluetooth stack that this company uBlocks has created. And then on this little board, there is also an antenna. So essentially, it's a self-contained processor with a Bluetooth stack on it, and then on top of it, you can write your own software. What Arduino people have done is, so they had kind of faced an issue, which is this is a very different processor than what classically Arduino hardware has used. So they could have ported kind of the whole Arduino software ecosystem directly on this hardware, but instead of that, they decided to use a real-time operating system that already comes is already available for this particular processor, and that's called Mbed OS. So Mbed is, just to give you a sense, and I'm going to just open my browser out here. So if you go to mbed.com, so Mbed is now operated by ARM, the company which makes the processor, and there were a whole bunch of things, including an operating system, and with a associated online compiler. So if you notice on the top right, there was this compiler button, and it, yeah, okay, I'm not going to log in, but it lets you basically go onto the IDE and all. But very importantly, it has a very rich ecosystem of hardware around it. Okay, so there are all these zillions of boards which support this Mbed OS, and the software itself they provide you the tools. They provide you a very nice, very solid Bluetooth stack, much better than what Arduino comes with. But very importantly for us, it has this Mbed OS, which is a very sophisticated OS. It kind of, we'll see later when we talk about software organization, it's what's called as a real-time operating system. Okay, and currently it is at version 6, but a lot of people still use version 5. Okay, so what Arduino did was they decided to use Mbed OS on this. And then they layered Arduino on top of it. And I'm going to tell about that later. But the bottom line is that you can use this thing as kind of this simple Arduino device if you so wish. But then under the hood, unlike standard Arduino, where under the hood is just bare hardware, here there is pretty sophisticated RTOS, and you can. This is still sort of work in progress at some level, but you can dive down into it and make use of the capabilities of that real-time operating system. Not entirely fully mature yet, and also this particular hardware lacks some debugging support that normal embed devices, embed hardware comes with, but it's quite a bit there. And so it's a pretty nice thing. You can use it in a dumb mode and you can use it in a sophisticated mode. As you would see from this, it has a whole bunch of sensors. So it has this 9-axis or 9 degree of freedom IMU. IMU stands for inertial measurement unit. So it's basically measuring accelerometer or acceleration, gyroscope, and magnetometer. Anyone knows what gyroscope measures? What physical quantity is measured by a gyroscope?
Acceleration.
Nope.
Angular rate of change.
Rotation.
Angular velocity, angular speed. Yeah. So the 3 axes. Whereas accelerometer gives you linear acceleration, right? So along the XYZ axis. And magnetometer, why do you think is magnetometer useful? So it gives us direction for sure. Do you think it gives some other information?
Change in magnetic field.
Okay, change in magnetic field, sure. What else?
Speed control.
Say it again, please. So it gives you three degrees of magnetic field, right? So you can also get how much, whether you are pointing up or down relative to Earth's magnetic field. So it's not simply telling you how the angle with respect to the magnetic north, but it's also telling you up and down relative to the magnetic field around the Earth. So collectively, these 9 degrees of freedom information is giving you a lot of stuff around it. Let me ask you the following: for a standard rigid body, how many degrees of freedom are there? How much information do you need to fully characterize where it is and how is it oriented in 3D space?
6.
So 6, right? Hopefully that's what you said. So 6 indeed. And here we have 9. So clearly there is redundant information out here, right? In particular, using acceleration and magnetic information, you can actually compute gyroscopic information, but you still use a gyroscope because it gives you less noise, right? Because to go from acceleration to velocity, we'll need to integrate. So in principle, I can get gyroscopic information out of the other, but it will be a noisy reading. Okay, so that's this. Then you have this proximity light color gesture. So there is a sensor out here, which you can use among other things for gesture sensor. And also I'm sure you have seen in some of the phones and all, you can kind of wave your hand and things like that. You can do those kind of games. And also, of course, measure ambient light. There is temperature and humidity sensor out here. They have an LED which you can blink to convey some information. There is a pressure information, and then also there is a microphone sitting out here. So you can detect sound and all. And then some of the interfaces, so you see these pins along the way, and when you buy the device, it actually comes with headers that you can solder. So you can also connect a camera to it. So a lot of people kind of do things like person detection or object detection kind of things around this. The processor here is what is called as a Cortex M4, which basically, think of it this way, that this among the microcontroller class things that come out of ARM, it's kind of at the high end, basically. Not the highest, but pretty close to high end. So pretty powerful processor with floating point unit and all. So this module internally, therefore, what it has is it has this NRF processor and then this antenna. So this particular module you can buy in kind of 3 different versions. The last digit here is 6. There's also a 1 and a 3, and they differ in their antenna choices. So in particular, this version 6, you notice is out here. So it has a PCB antenna. So essentially it's a self-contained unit. And actually, the chip itself here, this thing has a lot of other capabilities. So besides the Bluetooth radio, it also has a Zigbee radio. You would notice the processor is out here. So this is the ARM Cortex M4 processor. It has a lot of other stuff. So this is a radio part. There is some cryptographic hardware so that you can do secure communication. You have 1 meg of program memory and 256K of data memory. You also have PLL, so you can play with clock frequency and all. A whole bunch of timer counter stuff like that, an A to D converter, and NFC, so you can also play with NFC tags and all. And then again, kind of a whole bunch of peripherals on the right-hand side. So it's a pretty capable device, and you could do a lot of stuff. Oftentimes what happens is not everything is necessarily supported by the software that you may be using, in which case you just have to dive under the hood into kind of data sheet and the user manual of the hardware and write your own software. So very important when you're working with this kind of hardware is to read the very fine manuals that they come up with. So in this particular case, there are kind of 2 types. What is happening is there is a package, right, which is being made by u-blox, and then there is an internal chip, which is made by NRF. So there are 2 sets of manuals, and they have a fair bit of overlap. Both give sort of useful information. Okay, so I'm not going to go over those. Obviously, they're all on the web. But oftentimes kind of trying to understand them would be useful. So if you look at out here, these are the features of the chip, right? So it has Bluetooth 5, goes up to 2 megabit per second. Realistically, by the time you get rid of all the overhead and all, you will be getting around 1.2, 1.3, something in that range. It also has support for 802.15.4, which is what I call a Zigbee. Google has a set of protocol layers around these radios, which they call as Thread, which Google's products, Nest products and all used, for example. So it also has support for that. Let's see what else. You see a whole bunch of other details. For the radio, it also tells you very high accuracy of the receive energy. RSSI is receive signal strength indicator. What do you think we can use this for, RSSI? Like, why is it important to measure?
Positioning, maybe?
Pardon me?
Positioning, maybe?
Yeah, positioning. And more broadly as a RF sensor. So it turns out that with this information, you can detect things like people moving in the space. So positioning, absolutely, but there are a lot of other clever things you can do. In fact, with certain kind of RF sensing, you can even detect like respiration rate of people in the room and things like that. So there's a lot of clever stuff which in recent years people have been doing. Okay, let's see, what else does it have? A whole bunch of interfaces and things like that. Okay, so now, I mean, as processors go, it's a very nice one, but there are other companies who make similar kind of things. So it's not like there is sort of as a competitive space, I guess. Okay, so now, one of the things I wanted to go over is that given at least this this lower end type of embedded systems that we are looking at, energy and power considerations matter a lot. And that leads me to discuss about this issue of power management. Very common that computer systems and the components it's made of, they often provide lower power, reduced functionality modes. So you would see things like modes where you can stop various part of the processor, shut down the radio, power off the RAM, things like that. different peripherals, and then save power in exchange for a lower level of performance or a reduction in functionality, right? I mean, so maybe radio is turned off, for example. So this whole area is referred to as dynamic power management, okay? And it's been a pretty active area of research in this space, continues to be, and the operating system support for these. So for example, just to say, when one of the advantages of Arduino, which those Arduinos which use mbed, is that mbed comes with a very sophisticated power management under the hood. So those Arduinos benefit quite significantly from much lower power consumption than the standard Arduino software stack, for example. Now, so I can shut things down, right? So that's one approach. So this is shut down. Another thing we can do is we can scale the frequency. Okay, so essentially if my system allows me to change the clock frequency, and usually these processors can operate over a range of frequencies, then I can change those. And the main thing out here is that if you look at the power of digital hardware, then among other things, it's proportional to frequency. In fact, it goes something like this: it's proportional to CV square F. So this is capacitance, this is voltage, and this is a rough formula. It's not strictly this, but good first order, and frequency. So it's basically what is happening under the hood. If you go back to your high school physics, every time you discharge a capacitance, you basically are going, that charge is going to go through some resistance and rest of the circuit, and that results in dissipation of heat. So how much capacitance you charge, what level you charge it to, and how often you are charging, right? All these things collectively go on to dictate power. Power is energy per unit time, so that's why the F component is coming. So clearly, look, staring at this formula, I can say, hey, if I lower the frequency, then I'm going to lower the power consumption. It's not the full story, because usually there is some additional components of power which don't necessarily behave the same way, but the active power, when the system is actually computing, that component of the power behaves like this. So this is called as dynamic frequency scaling. And of course, I can reduce the frequency very low and correspondingly reduce the power, but it will come at the cost of performance, right? I'm going to do things slowly. So what do you think will happen to energy? So this is a story of power, right? If I reduce frequency, what do you think will happen to energy?
It will not change.
Yeah, it won't change. In fact, worse yet, it won't change because essentially I'm going to integrate over time, so F and T will cancel out, right? I mean, so energy is CV squared. In fact, it's worse because this only represents the dynamic part of the power consumption. As I mentioned, there might be some static terms, so there might be some P static. And that will now increase, right? I'm going to be burning static power over a longer period of time, so I'll burn more energy. So energy may actually increase as a result if I operate very slowly. So the most sophisticated form, so the first one was shutdown, second one is frequency scaling, and the most, and frankly, frequency scaling is really not a serious way, right? I mean, why would I do frequency scaling? Think about it, right? I might as well just run rapidly and shut down. Voltage and frequency scaling together is the most interesting one. So if I stare back at this formula, so voltage is a square term, which basically means that if I am able to reduce the voltage, then I actually get a quadratic improvement, and actually, depending upon things, maybe even more. So I can play that game. Now, as you reduce the voltage, the hardware operates slowly. So you reduce voltage, and then the frequency at which you can operate at will also get capped, right? So I can maybe operate at 100 megahertz at let's say 3 volt, but at 2 volt, maybe I can only operate at 50 megahertz, right? So I also have to kind of keep that in mind, that every voltage will have a corresponding maximum speed at which I can operate. So what you really have is a knob which controls frequency and voltage, or another way of saying is controlling power and speed. But what is also happening as a result is, if you're playing these games, the energy begins to go down, because as I am lowering the speed, lowering the frequency, so let me just go back to the slide. As I lower the frequency, I can also lower the voltage. So even though when I integrate, my delay, my time to execute goes up proportional to 1 over f, but I'm still benefiting from the reduction in voltage. So I come out ahead on energy, but I'm running a slower system. But since my reduction in energy is going to be quadratic, then the game I can play is, perhaps I can add more hardware. I can pipeline, I can parallelize. Okay, so I can put basically multiple processors. So that's what happens out here, that we basically combine these methods with architectural mechanisms, as in adding hardware, extra processors, a multi-core processor, for example, and then still come out ahead. So I maintain the speed, lower the power, and come out ahead. So this is called dynamic voltage frequency scaling. It's the most sophisticated form of power management, but it does require support from the underlying chips and boards and whatnot, because you have to be able to change voltage and frequency in a coordinated manner, and to be able to do so in a very efficient manner. You don't want things to take lots of time to change the voltage or change the speed. Now, changing frequency is easy. In fact, even the chip that we had out here, right, this one, we already see these PLL, which stand for phase lock loop, but you can loosely think of them as a way to change frequency very nicely. You can lower the frequency, you can increase the frequency. So PLLs give that ability to you. Voltage requires more effort. So actually, going back out here, this part that you see, this is the voltage regulator. This is what takes the voltage from outside and then converts it into a clean voltage. So this regulator now needs to be able to supply different amounts of voltage to rest of the chip. I will leave you to sort of find out whether this chip allows dynamic voltage or not. Many do, many don't. Most don't, but many of the newer chips do. Okay, so we can do this dynamic voltage frequency scaling. So these are kind of the 3 main techniques which are out there. And essentially the middle one you can scratch out, not terribly useful. So it really boils down to shutting down, as in run as fast as possible and go to sleep. And the second one is run as slowly as the time permits, and then adjust the voltage and all accordingly, right? So, so whatever, run fast and sleep, and run just at the right speed. Now, which one works better depends upon the characteristics of your system. So if this component, the static power consumption component, which is not being governed by this voltage and all, if this is large, then I'm not going to benefit from DVFS, right? So this voltage frequency trade-off will not matter, right? I mean, if the second term dominates, then my better strategy would be run as fast as possible and go to sleep. If on the other hand, this component dominates, CV square F, then DVFS is going to help you. In that case, you operate in this mode. Okay. So it kind of depends on what kind of system you have. As technology has changed, it used to be that DVFS is the place to be at, but oftentimes you find that running as fast as possible, like finishing the task as soon as possible and going to sleep, matters. And in fact, even more, you want to maximize the sleep time, because it takes some time to go to sleep and wake up from sleep. So operating systems do a lot of effort towards clustering activity so that they are not waking up needlessly. So you would see optimizations of timers and things like that, which operating systems do. Often, like in Linux, you would hear something called tickless timer, and Mbed also has a tickless timer. Kind of the idea is, if you're going to sleep, then try to sleep as long as possible. Okay, don't let the OS wake you up. Don't let the clock wake you up, for example. So a lot of optimizations which are done towards that. Okay, any questions on this? Is it okay? So let's see. So some other courses in CS and ECE do cover some of these things. Occasionally, I teach this course 202B, which kind of goes more in depth into energy management and all. Okay. Now, what about our processor? So if you look out here, it has lots of interesting capabilities. Okay. So firstly, it can accept a large range of voltages. So if the surrounding board has the ability to change the voltage, it can benefit from it. Okay. It has low current modes to save power. It can wake up very rapidly. Lot of power management of the peripherals. It takes care of it in hardware. If you don't need to preserve the data, then it can sleep very efficiently. 0.4 microamp at 3 volt, which is 1.2 microwatt. Okay, so pretty good power consumption characteristics. Okay, and then you can also set it up so that the system is kind of on, and it can wake on a real-time clock, in which case you burn another factor of 3 to 4 power. So you'll find that in this is just an example. I mean, you'll find that embedded processors tend to have some pretty rich variety of modes. And in fact, this is just a glimpse. Under the hood, what happens in this processor is that there is this thing called PMU, Power Management Unit. And what it does is it interacts with the voltage regulators and the oscillators, and then correspondingly manages the state of the CPU, state of the memory, state of the peripherals. The idea is that it automatically at all time tries to keep the things that need to be active and puts other things to sleep, and try to operate them at the lowest power mode. In the instruction set of these processors, usually there would be some sort of an instruction which say go to sleep mode or go to deep sleep mode, and there may be more than 2 sleep modes, and then wait for an interrupt or wait for something to wake you up. Okay, so there would be some sort of a instruction which would be like wait for interrupt. So you go to sleep, and then arrival of a network packet or some other interrupt signal like a timer or some sensor going on will kind of kick the system out of the sleep mode. And then if you dive further, these are just things extracted from the data sheet. You would see that they kind of characterize how much current is being consumed in different modes. So you would see there are a whole bunch of different modes corresponding to what is happening to the system, what is happening to the RAM. So you would see whether the system is on or off, whether the RAM data is being maintained or not, when can you wake up, all those kind of issues. All those kind of aspects result in a bunch of different modes. So there's a whole bunch of these different power states that exist, and it's a job of the software, or specifically job of the operating system, to deal with this. Okay, now what you see out here is on the left hand side, you're seeing when the system is off, there is no RAM retention, and the only way you can wake up is if the system is reset. On the right hand side, you are seeing system is on, no RAM retention, but you can wake up on any event, okay, like some interrupt or something. So one thing you see is the right-hand plot consumes more power, right? I mean, if you just look from the scale, this one is going to 12, this one is going to 4. What you also see is power consumption at 3 different temperatures, minus 40, 25, and 85. So what's the takeaway here? If you're operating in a higher temperature regime, then your hardware consumes more power. So cold temperatures, you are better off, okay? And this can actually lead to some interesting things. If as you burn power, if you don't remove the heat which is coming out, then that heat is going to remain trapped in the package and is going to increase the temperature of the electronics more, and the electronics will consume more power, and the temperature will go up even more, and kind of you end into this kind of a thermal runaway, okay? So it's very important that the hardware side of the design team should design things so that the heat is removed, okay? Otherwise, you run into essentially thermal runaway, the temperature will rise very high, and then either the system will shut down if you have so designed it, or worse yet, it can just destroy itself. Okay, then the final trend line that you see out here is that what happens as the voltage increases, right? So as you go, as your voltage increases from 1.6 to 3.6, on the left y-axis is current, right? So you see there is a mild increase in the current. But remember, very important, current is just part of the story. Power is voltage times current. So what is happening is, as you're going from left-hand side to right-hand side, your power consumption is going up, right? Quite significantly, almost like factor of 2.5 or so. So oftentimes you see data sheets just report the current number, and people just use that as an indication of power. But always remember, voltage matters. And there is a slight dependence on of current on voltage still. And then to add to all of this complexity, you also have to take into account what happens to the power supply. Because power supplies or batteries, right, they also have inefficiencies. So they will also have a sweet spot. So very important, kind of like the overall system be designed for maximizing lifetime or whatever consideration that might exist. So it's kind of a deeper story on the hardware side. Looking at the software from a software viewpoint, from the system management viewpoint, kind of these first order models are sufficient for our purposes. So any questions? So again, remember, power versus energy, different. Current by itself is only half the story. And we have these 3 very broad methods. Shutting down, reducing the frequency, which is largely useless for the most part, and then simultaneously reducing frequency and voltage. And generally your goal is to have acceptable performance or whatever, meet the deadlines while minimizing energy or power. So let me ask you the following. What is more important, reducing power or reducing energy? Or under what circumstances do you think one is important versus other?
Power will be important from the point of view of heat dissipation, and energy would be important from the point of view of battery life.
Yeah. So energy is battery life. Energy is also the primary determinant of cost if you are operating off power supply, right? You are billed in terms of joules or kilowatt hours or things like that, right? So essentially it affects the battery size. Power affects the heat dissipation. Power also, in addition to what you said, it also affects the size of the battery you are going to use, or if you're a system connected to electrical wiring, then the size of the wire, right? I mean, so for example, if I try to draw 1 watt of power from a tiny coin cell, then it will either fry or will be extremely inefficient. So when a battery tries to supply power at a rate higher than what it's designed to sustain, then basically you are pushing it, right? It's kind of like driving a car at extremely high speed, and then it will burn more, right? It's going to be less efficient. But to the first order, what you're saying is absolutely right. So Now, heat dissipation in many applications is pretty key, right? Because I refer to, if you don't remove the heat, then you have problems in terms of damaging the system. And in some cases, also damaging the environment, right? Imagine something which is implanted or something which is touching your skin. If it gets too hot, then there are biological consequences to that. So power and energy both matter. Energy is on the primarily affects the battery size and all, and power primarily affects the packaging and all those kind of considerations, but they are interlinked. Okay, so so let's see how it also plays out in a different way also. So what I've shown out here are two processors, and they're pretty old, but just I have plots for them handy, but they just serve to make the point. So there is a high-end ARM processor made by Intel when Intel used to make it. They don't do anymore. And then there is a very low-end microcontroller. One is 32-bit, another is 8-bit, one is 1 watt, the other is 50 milliwatt, one operates at a gigahertz, the other operates at 10 megahertz. And the question comes, which one is better for a low power system? So naively, you might say, hey, the right-hand one, look, it's only 50 milliwatt versus 1 watt. But we are ignoring how much work it's capable of doing, right? I mean, it's 8-bit versus 32-bit. It's operating much slowly. So depending upon the computation and how often you are computing, either one of the be better. So just to make the point, there are three different compute scenarios that are here. One on the left-hand side is doing a fast Fourier transform. Middle one is just checking the cyclic redundancy checksum on some network packet, let's say, or a file. And the right-hand side is FIR filter, just some signal processing computation. And in each case, the left plot is on the little microcontroller, and the right plot, the right bar is for the big processor. And the y-axis is energy and in microjoules, and these are on log scales, as you can see. So as you can see, in terms of energy to do the same task, the little processor is far worse, right? So if battery size was a consideration, and not latency. If battery size was the bottleneck, then clearly I'm better off on the left-hand side. Now, often what happens is you may have a deadline, in which case you might want to operate in that mode, right? But on the flip side is that just because by using the right-hand processor, you may end up into a situation where to supply that 1 watt, you may just need a more expensive power supply system, a less efficient power supply system, and also the bigger story can be more complicated. But the answer to this question, which one is better for a system where power or energy needs matter, the trade-off may not be often that obvious. So looking at this way, computation, energy taken to do some computation, clearly it seems like big processors are better because they just have an architectural advantage. Okay, but the flip side is that various actions such as changing clock frequency, putting the processor to sleep, all of these things become a lot more inefficient with the big processor. So what you have on the left-hand side is how much time and energy it takes to suspend to put the big processor to sleep mode, and it's tens of microseconds or even a couple of 100 microseconds. On the other hand, the very right plot you see, we can go to sleep and wake up much more easily. Now, some of these absolute numbers don't put too much value in it because they keep improving, and like I mentioned, these are somewhat older processors. But the fact still remains that if you try to put to sleep a system running Linux, for example, it's a very different thing than something which is running a tiny little operating system. In one case, it will take tens of clock cycles to put to sleep or wake things up. On the other hand, the other one, maybe it's a less complex system, less complex operating system, less complex application, less state. So all of those things kind of come to play. So generally speaking, systems where you need to wake up very frequently and go back to sleep. So in order to realize our strategy of run as fast as possible and go to sleep, It may be that the little guy, which is less efficient computationally, as you can see out here, may come out ahead. So the overall picture really is a function of what you are computing and what's the schedule of computation, right? I mean, are you continuously computing, or are you in between going to sleep, and how often is the task arriving? All those kind of questions matter before one can truly answer which one is better. And then, of course, the other issue is, what am I optimizing for, right? Am I optimizing for battery size? Am I optimizing for something else? And also what my performance requirements are. So very complicated story. And so resist the temptation to simply say, hey, the lower power processor is better. Usually it is not. So what do we do in this setting? So how do we, so clearly kind of the objective, the goal that we have in mind can be pretty complicated. One goal which people have articulated, and this comes from a famous paper out of Google in context of data centers, but what they define as a reasonable goal is energy proportionality, okay? And what it basically says is that we would like our systems to consume energy proportional to the work they are doing. So if I ask the system to do less work, it should consume less energy in any given time window. If I'm asking the system to do more work, then it should consume more energy in a given time window. In particular, if I'm not asking the system to do anything, it should not consume anything. And if so, it should basically scale with respect to that. And almost any system that we can think of usually has some bursty behavior of workload. Okay, there are cases you can imagine where a system is facing a constant workload, but usually it faces kind of a time varying workload. So for example, if you look at what the CPU on your smartphone might encounter, it's a pretty complicated mix of things. You have widgets on your home screen, and you have background tasks running, and then of course the front task you are doing. So if you profile the power consumption on the CPU of your phone, it will look something like what this plot shows, right? I mean, the clock animation, every time the user swipes, something happens. Every time you say some wake word to your phone, things happen. Maybe there are on the background, it is collecting some health related sensor data and processing it. So kind of a pretty complicated thing. And what you would like to do is, you would like the compute system, or actually the whole system, to kind of scale in proportional to the demand that is being placed on this thing. So what that leads to is that, or what it has led to now in past 6-7 years, is a more complicated compute system. And the challenge is the following: as we kind of saw, I mean, one takeaway from the slides is that for heavy workload, big processors are good. Whereas for small sporadic workloads, the tiny processors are good. So what systems began to do some years ago is to really combine the two, okay? So you take a big processor, and it will have some regime of applicability. Okay, so this big processor, I can do some dynamic voltage frequency scaling, but it will have, since it's designed for high performance, then if I try to operate it on a very low performance regime, it will kind of plateau out. It will have high baseline because it's just big hardware, lots of electronics, lots of transistors and gates sitting there burning power. So in this regime, it will not be good. Whereas in the high performance regime, I will have some scaling with DVFS, and that's where it shines. And then what we do is we combine it with a little processor. And this little processor is optimized for a lower level of performance. And therefore, it would be a simpler processor, less baseline power and all. And therefore, its regime of applicability would be somewhere lower. And then you combine the two, and the idea is that this whole thing now behaves as if I have a processor which is optimized over a wider range. So if you listen to presentation, whatever descriptions of processors used in iPhones and Samsung phones and things like that, you would see that they often talk about how they have whatever 8 processors, 4 of which are big processors and 4 of them are tiny processors and all. So what you find on the modern chips in smartphones and embedded systems are these combination of processors. And to make things invisible to software, the 2 cores are usually picked to be of the same type. That is, they will have exactly the same instruction set. It's just that the implementation is very different. So like, for example, the big core may have deeper pipeline. It may have more larger number of arithmetic logic units so that it can execute more instructions in parallel. It may have a bigger cache. So those kind of things. So from a instruction set architecture perspective, both the cores will have exactly the same view. You can take literally the same software and run it on either one of them. But all these microarchitectural details under the hood stuff, cache and number of ALUs and these kind of things, they vary. And that's what makes things kind of different. So you would find, like, for example, on smartphones, typically ARM's A series processors are used, and ARM makes a whole bunch of A series processors. And usually, like, they might combine kind of a high one and a low end one into the same chip, and then have several of the high end ones and several of the low ones. Several of the high end ones, partly because the workloads have increased, but partly also, remember I said earlier that it is better for me to operate slowly and have more hardware because of the DVFS effects. So it's better to have more cores operating slowly as opposed to a single core operating fast in general. So by spreading, parallelizing and operating at a more efficient level kind of pays off. So what happens is that the operating systems now have to do this constant juggling of whether to use a big core, large, small core, how many big cores, how many large cores. And then the hardware side has to worry about how do I, in the face of all this complexity, how do I deal with things like, as computation is to move from one core to another, how do I take all the states? Maybe my interrupt handler was sitting in the small core. Now suddenly that I transferred burden to the big core. I have to transfer, I have to take care of all that IO now going to the big core. So there's a lot of hardware level housekeeping that needs to take place, reroute interrupts and IO to the right place, make sure that the caches are kept in sync so that processor performance is not affected. All of that magic goes on the hardware level. So it's a lot more complex than simply, hey, let's just put some more processors. There's a lot of other stuff which goes on in order to achieve this. So kind of the idea now is that as a consequence of this, I basically have this plot which looks like a longer straight line, so kind of towards our goal of energy proportionality. Okay, so the idea, one way of thinking about it is, our individual components or subsystems are never energy proportional over the range of performance that we need. So we get the illusion of energy proportional system by using many such many components and then shutting them down as the case may be. So like in a data center, I may achieve an energy proportional data center by being very clever about which servers I keep up, right? I may have 100 servers, and then as the workload comes, I activate them or put to sleep. Maybe what I can do is I'll have enough servers to meet my current demand, and then I'll keep 1 or 2 servers up and running, ready for a demand surge. Or maybe I'll do some prediction of the demand surge. So people do all sort of clever things in software and algorithms towards this goal of energy proportionality. So very hard to achieve because it's very hard to design a single piece of electronic which can be energy proportional over a huge range. But by appropriately managing them, you could achieve that goal. Questions?
Does the user have access to like all these features, or is it just too much and the OS does all this management?
Depends on the OS. So in Linux, actually, you do have a fair bit of control over this. In particular, you can pin processes to specific cores. So you can exercise control over it by that. So you can say this particular process or this particular thread tie it to this particular core. So you could do that at the user level, as in it should be a privileged user, a user with root privileges. You can even do this thing in Android, because Android, as you know, under the hood is Linux. So if you know what you're doing, you can kind of dive down. Okay, I mean, obviously most users don't do it. It's kind of a different story. But like, for example, in projects in this course and others, I have had many students kind of dive to that level. So it really depends on the OS. Yeah. Okay. Now, philosophically, some OSs basically say this is something that OS should not expose, and there are two reasons for it. One is that they believe that the users may not do it correctly, as in there may if we expose this power management to the application, then it will blow it, and there are cases of that. So for example, certain power management features which are exposed in Android resulted in bugs, relating application created bugs which resulted in excessive energy consumption. Okay, so actually Google moved away from it. Apple, philosophically, as you might guess, sort of has been in the other corner, which is OS should do it. Another reason why OS should do it is OS has the big picture, right? It knows what all the processes are, and also any given application can only have a myopic view, right? It just knows about itself. So the system state is only available to the OS. So one can also say that a more informed decision can only be done by the OS. But having said that, I mean, like I said, there are some operating systems do give you control. Any other question? Okay. And then, so in this case, the two cores were exactly the same, right? I mean, as in exactly the same in terms of the instruction set architecture. Often these architectures are coupled with then also processors, which are even more efficient, but perhaps more specialized. They may have a different instruction set. Like, for example, maybe these may be ARM A, like these two cores, and this might be a signal processor or an ARM M series processor, right? So more specialized, more loosely coupled, in the sense that obviously I cannot take a software running on the main cores and put it into the processors or vice versa. But you could conceivably program it. So for example, if you have a Android phone based around Qualcomm Snapdragon chips, then the Snapdragon chips have ARM-based main cores, but they also have something called Hexagon DSPs. Okay, Hexagon DSP on Qualcomm chips. And usually data from sensors and microphones and all kind of heads to that Hexagon DSP. And you can, initially they didn't expose it, but in recent, whatever, 5-6 years, they basically make it visible to ordinary users. As in, if you write code, you could actually write code for that DSP. There's no operating system there. It's a very different beast. You could think of GPUs in the same vein. Nowadays, many processors have neural accelerators for neural network, accelerating neural network computation. So you begin to see a variety of specialized processors, sensor hubs. Sometimes they are not exposed. So if you look at a typical modern SoC, embedded or mobile SoC, they probably have several hidden processors which only the handset vendor or the system vendor gets to program it. You as a user don't get to see it. On Apple's chips, for example, they have this thing called motion processor, which is actually a Cortex M core on which they process the IMU data. So or at least it used to be a Cortex-M core. I don't know what it is now. So there are these specialized processors, more loosely coupled, sometimes user programmable, but kind of the idea is that they are taking care of either this end, actually, and sometimes they're at this end, very high performance, but maybe bad example. They might be at this end, but they seek a lower power, but at the cost of specialized. The neural network accelerators are like this. They really are aiming for very high performance at a lower power relative to what you might achieve out here, or they may be residing out here with a lower power, but they are specialized. So all of these, so if you look at these modern systems now, then it's kind of, you have these choices, right? You may have cores which are mutually replaceable from a software viewpoint other than performance, and then you have these specialized cores which again, I guess you could do equivalent computation, but you cannot take literally the same code. So you can run a neural network on these main cores, or you can run the neural network on that specialized neural accelerator. Vastly different performance, but your neural accelerator can only do that one thing, not really broader range of computation. Okay, so with energy proportionality, and if your OS and or application or hardware are doing its job correctly, what will happen hopefully is that when there is burstiness, when there is more load, then the big cores kick in. When there is little going on, then the tiny cores kick in, and you would never notice. Sometimes all this power management goes awry and system doesn't do very well. So I think two generation ago, Qualcomm chips, they had some issue and they were insanely power inefficient, right? They basically go into some sort of a runaway mode, and they had a huge problem. So that they fixed that since. But getting this power management right is extremely important, because your devices are really thermally constrained and battery constrained. So extremely important for one to get this thing right. So this is an example of a big dot little chip. It's a few years old, but essentially you would see the same thing with newer chips, that in this case, you have 4 A15 processors and 4 A7 processors. So A7 are the little ones and A15 are the big ones, okay? And same instruction set, but different microarchitectures. And in particular, A7, which is a little one, is an in-order processor with 8 to 10 stage pipeline. In order means all the instruction sets which are all the instructions which are coming are executed in the order in which they appear in the program. There is a single queue and there are 5 execution units. And as a result of all of this, on an average, it computes 2 instructions in any given clock cycle. A15, on the other hand, it has a much deeper pipeline, 15 to 24 stages, out of order execution. So what it does is it continually examines what are the next instructions. And it's possible that maybe I cannot execute the next instruction, but maybe I can execute the one after it because it doesn't have any data dependency. So all that smarts is there so that it can do more parallelism. It can execute more instructions in parallel. As a result of it, it can execute 3 instructions in parallel, typically. And it has 8 execution units. So as you can see, while the instruction sets are the same, one core is a lot more capable, but obviously at the cost of more transistors. So it would be setting its baseline power is higher, and so it's optimized for performance or power at a higher performance level, whereas A7 is at the other end. Okay, so this is pretty routine stuff, and you certainly see it in your phones, but in a lot of other embedded devices. Where your Raspberry Pi, for example, is quad core. Okay, the Raspberry Pi 4, for example, is quad core. A lot of other similar things also have microcontrollers in them, so they have some equivalent of this. And I mentioned neural accelerators. So many of these things are not specialized processor for accelerating convolutional code, convolutional operations in a neural network, for example. So a lot of architectural stuff kind of kind of stuff which is going on in order to achieve these objectives. Okay, so all of this naturally raises a question: how do we manage these things, right? And of course, as you can imagine, there is tons and tons of work on algorithms which seek to manage the tasks. And one of you asked the question, can the user do it? And yeah, in some cases, the user can do it. In Linux, there is a concept of governors, okay? And kind of the idea is that these modules in the operating system, governors, they are in charge of the scheduling algorithm, which is used to control the voltage frequency of the processor, as well as moving things around among the cores. By the way, the same student who asked me about whether user can control it, user can actually also control the frequency and the voltage in case of Linux. Okay, so you can do a lot of games, and you can destroy your system if you don't do it right. But it boils down to the OS to kind of do it. So there's some sort of intuitive approaches you can imagine. One thing I can do is I can track a weighted average of the CPU load, right? So I can look at the recent history and I can say, what's the average load on the CPU? Operating systems typically have a well-defined version of CPU load, but you can effectively think of it as, in the recent time window, what fraction of the time was the CPU actively doing something, right? Because oftentimes things, it's not the spinning wheels running a no-op instruction. So what I can do is I can say, okay, if my big processor is being underutilized, then I can basically move to the smaller processor and vice versa, right? So you kind of keep tab of what the task load is and have some sort of a threshold. So on this diagram, what you are seeing is we are tracking the load using this pinkish purplish color plot, this one. And then based upon that, we kind of decide at some point that we are going to switch to a bigger processor. So in this case, the example being I have one little processor and one big processor. So it's a simple scheme, but it has a lot of problems, right? I mean, it is always reacting. And oftentimes you may have tasks which have some pattern to them, and also maybe you can exploit it. Also, this is clearly just working for one task, and also might have more complicated behaviors that your task mix can be showing. But even these simple schemes often yield good results. Okay, so how much saving that you may have as opposed to just running it on a big processor, or how much performance loss you have if you're just running on a little processor. So one can account for those kind of things. So a pretty well studied area in recent years with lots and lots of work and fine tuning, and also taking into account one of the things that people have explored is, can I personalize things to a particular deployment? What I mean by that is, the workload I do on my phone is presumably quite different than the workload you may be doing on your phone, right? So maybe the scheduling should adapt, personalize to better. So it learns how to predict my workload demands, and the software on your phone will learn how to predict on your demand. Many these simple control schemes have given way to predictors which are based on neural networks, and also they try to predict what should I be doing. So essentially, machine learning methods being used as part of this power management. So it's been one of the more, let's say, hot things to study in recent years. Now, and another thing is companies like Apple and Qualcomm and all, they collect a lot of data from your usage, and based upon that, they try to come up with better and better power management strategy, right? So essentially, they may start out with something that they push out, but then over time, based on the actual usage out in the field, the goal is to come up with a better scheduling algorithm, a better way to power manage. So, so that exists. Higher end chips, as I said, nowadays have accelerators as well as these other specialized processors, so DSPs and things like that. So, a lot of complexity something that software, if it so chooses, can exploit. Okay, so that was on the compute side of the story. Rest of this lecture, I want to do a quick sort of level setting on other aspects that exist in the merit system, just so that as those of you who are unfamiliar, at least know what goes on in hardware. But before I do so, questions. Okay, sounds like none. So let's move on. So what I want to do now is to sort of go over, let's see, nothing in the chat either. Okay, great. So, so let's talk a little bit about what kind of things otherwise exist on these microcontroller and embedded processors and which one can use. So obviously computation by itself is not terribly useful. So you also need to do IO and communication. IO basically refers to communicating with peripherals and all, and communication, loosely using it in terms of talking to other computers, right? So sometimes same mechanisms are used to talk to both. And also often peripherals and radios and all really are part of the same chip, because we really have a system on a chip. But these are, besides computation, this is very important. In fact, in a typical embedded system, much of what you do is actually related to IO and communication. So variety of IO devices, don't need to go into it. Main point is that they're pretty diverse. Very varying data rates, latency requirements. You often need to synchronize, and you may have very different ways of accessing them. These peripherals can be pretty often quite a bit of pain to deal with. And the flip side is you also have a lot of constraints. You are operating with very constrained, resource constrained devices. So very commonly, the kind of things one has to do when interacting with, for example, let's say sensors and actuators, you may have to get and set some parameters. Okay, so usually these devices may have some registers, like to set the sample rate of the sensor, to get the next sample, all those kind of things. You may have to transmit and receive data, so which might be with the serial port or with a radio, those kind of things. And then there might be power management type functions and some other stuff, right? I mean, so these are the typical things that one might expect processor to do with the radios and the sensors and the actuators and whatnot. So from a software viewpoint, there are two ways typically IO is made visible to the software. One is by putting the device into memory. So it literally appears as just a specialized area in your address space. And the other is that the device has some specialized registers and you access them using some specialized IO commands. So, so the reason these things matter is kind of a mix of things. So regular data, which resides in a regular data memory, we can cache, right? There's a data structure, I can cache it into my cache memory. Those of you who don't know what cache memory is, it's just a memory where you temporarily fetch the data so that it's faster to access it. And then you operate on it, but when you write to that data, you are just writing to the copy of the data in the cache. You are actually not writing it all the way out into the memory. But that doesn't work for IO. I cannot cache the IO, right? Because if I have to write a piece of data to, let's say, a digital to analog converter, it does me no good if I write it to the cache and it doesn't make it to the device. So IO devices do differ in this regard. Timing matters. When I write, oftentimes these devices may say, you write and then the next write should happen within a certain time. That's not true for a data structure sitting in my main memory. I can write one field and then I can wait some time and write another field, and it's okay. But a lot of IO devices have timing constraints of this nature. Another issue is that reading and writing can cause side effects. So many times you will see these sensors which will say, every time you read the sensor, maybe some counter inside the sensor will advance. With regular memory, that's not an issue. I can read memory location number 10 once and read it again, no big deal. Just reading some memory location. I can't undo the effect on the physical world. So if I have a memory location, I write to it, and then if I realize I messed up, I can overwrite it. No big deal. On the other hand, if it's an IO device, if I write to it, that may have caused the robot arm to move, and I may not be able to undo it. So just we have to be aware that IO devices, communication devices have an additional effect. It's not simply bit changing in memory. And then finally, you do have to worry about sharing across applications. If you have multiple applications and they're sharing the same radio or the same robot arm, it's a lot more tricky situation to work with. You have to kind of have some well-defined product strategy to share this thing. Against standard stuff sitting in memory, doesn't face these issues. So IO is trickier, and there are a couple of ways one deals with this thing. One is in some processors, there are specialized IO instructions. And Intel processors, Intel x86 processors are an example. They have these instructions called in and out instructions, which are meant for accessing a separate area, which is a separate sort of IO ports. So IO devices are not part of your main memory, are not part of your regular address space. They are kind of sitting separately, and you access them using these IO instructions. And very importantly, on these processors, if you're using the right OS, then only the OS can issue those instructions. Regular application cannot. So for an application to talk to an IO device, it will have to give yield control to the OS, and then the OS will do that. So these IO instructions are only available. Pen has stopped working. Just give me a sec. Okay. So only the OS can do these kind of things. Now, having said that, Intel x86, while there are embedded versions of it called Atom, they're not terribly common in the low power regime. Okay, you'll find them in biggish embedded systems, but that's where they kind of end. So while these IO instructions kind of thing exist, what you will find more common is the approach that other processors take, which is IO is mapped into the memory. So the same data memory space where your data reside between some address, some part of it is set aside for IO. And kind of the idea is that your IO devices are nothing but some address location in your memory. But now you need to be kind of careful. All those issues that I talked about, can't cache, timing matters and all, you have to make sure that caching part in particular, that you make sure that this area of the memory is not being cached, because otherwise you think you are writing to that device or you are reading from device, but all that is happening is you are reading or writing from the cache, and that's no good. But doing this results in much cleaner software. So this kind of stuff, because I'm treating everything the same way. I can think of this area of memory in terms of a data structure or a class object which is mapped to it, and just my software becomes a lot more elegant to write. Now, these details, depending upon what kind of OS you are using, may be hidden from you, in the sense that if you're using a rich operating system, then the device drivers, a layer of software which deals with IO devices, hides all of these things from you. On the other hand, if you are working with what is called as bare metal software, as in there is very little OS or no OS, then you have to make sure you are familiar with all these details, and your application software will have to kind of deal with it. And in order to do so, you'll have to kind of occasionally or quite often consult the hardware device data sheet also in order to do that. So which one is better? Well, depends, but generally speaking, I think the second strategy has won, in the sense that's what you will find. I think it's a lot cleaner strategy to work with. So what else? Well, you will find that these devices that we are using, including the Nano 33 BLE, they have a whole bunch of what are called as GPIO pins, so general purpose IO pins. And they basically are pins which are in logic 1 or logic 0 state, and you can manipulate them in software. You can connect sensors to them, LEDs, things like that, actuators. And essentially in software, you can control them. You can even do a lot of complicated timing and all around it. So one of the advantages of these embedded processor is that you can do very precise timing. You want to generate a specific waveform to control the rotors on your drone, you could do it. So it's called bit banging. I can essentially do bit level precise timing by making use of low level software and real-time operating system features. So one of the challenge when you are writing complicated software for these devices is you don't have a screen on which to print pretty messages, or even if you could, it will disturb the timing. So oftentimes what happens is, to be able to debug, you output signals on these GPIO pins and then monitor them using some hardware. So nowadays, for fairly cheap, you can buy hardware which connects to the USB port of your computer, and then much like an oscilloscope, it basically can monitor the I/O of your devices. In fact, one of the things you can also imagine doing is getting a second Arduino and using that second Arduino to monitor your main Arduino, for example, right? So you can, if you're outputting the signal, well, that other Arduino can act as the monitor and controller for it. So I often do that. Okay, so instead of spending money on a scope and all, you can use just a second embedded device in that role. But you can also buy, one can also buy very cheap, some of the stuff out of some sort of international stores, particularly in China. I mean, you can buy kind of low-end stuff with reasonable software and all for like 30, 40 bucks, and they give you the ability to monitor these things. So that kind of stuff is very common. These things also have analog I/O pins. So the particular Arduino that I'm making you purchase only has analog input, so A to D converter. It has a pin which has it has an A to D converter, and which allows 8 pins to be connected to it. So you can monitor 8 analog signals. And when you are dealing with analog, unlike digital, where you just have a 1 or a 0, here you also need to worry about the number of bits in which you are going to digitize the signal. So you have the analog input coming in, and then certain number of bits going out. So bit resolution is one parameter, and how often you are sampling. Are you sampling periodically? Are you sampling asynchronously, as in only when needed, on demand? These are kind of two main ways you can approach it. Let me ask you the following. For a signal like, I don't know, let's say sound in the environment, what do you think is a good bit resolution? So remember, the more the bits, the finer the signal you can hear, right? I mean, 1 bit corresponds, it's like the sensitivity. So if you have played with Arduinos and all, what do you think is the typical bit resolution that you encounter? Rough ballpark. Is it like 4, 5? Is it like 8, 10? Is it like 20, 30? What ballpark?
Like 8 to 12, maybe.
Say it again, please.
8 to 12.
Yeah, 8 to 12. 12 to 14 would be a good one. Beyond that, you are basically, you will not find in these cheaper devices. On the other hand, if you are doing some very sensitive applications like seismic signal monitoring or something, you'll probably pay for some pretty sensitive A to D converters of like 20, 22 bits, things like that. But more typical in low-end embedded systems, sometimes you'll find only 8 bits or so, very typically 10 to 12. And then there is a sampling rate. So how do we decide the sampling rate? If you are monitoring something, How do you decide what sampling rate to pick?
Based
Depends
on the
on
based on the frequency of the signal you want to sample. So at least twice
so
the
based on
twice the frequency.
twice the frequency. So that's what we are taught, right? I mean, in our undergrad courses, Nyquist rate, those of you who are in computer science may not have heard of it, but basically one of the well-known things which comes from Nyquist and Shannon is that if I have a signal whose frequency goes up to some value f, then in order to sample and still be able to reconstruct, rather than not lose any information whatsoever, I should sample it at twice that frequency. That's true, but it's a sufficient condition. It's not a necessary condition. So in the past 15 years, 20 years or so, a whole field has emerged which has been looking at smarter ways of sampling. And intuitively, if you think about it, we sample, let's say, a speech signal, but after that we are able to compress it. So clearly, I was sampling redundantly, right? If we sample it using the Nyquist rate, using a 2F formula, but then we compress it. So if it was truly the minimum sample rate that was needed, then I should not be able to compress it, right? So what is going on under the hood is that we are not making use of information about the signal. We are really, other than the fact that what its upper frequency is, and also we are not, our goal may not always be to reconstruct the signal. Maybe we have a more limited goal to detect something, okay, for example. So newer sampling strategies can do much better, and I think later in the course I'm going to talk a little bit about those. Again, this is where smarter sampling, some of it is driven by ML algorithms and all, have begun to come into play. You also have output, analog output, so that you can generate analog waveforms. And in order to do all of this, you also need, in order to deal with the analog world, you will often need additional analog components. So usually these chips may have some of it. So for example, if you are feeding input to the A to D converter, and one of you just said we sample at twice the frequency, twice the maximum frequency, but how do I make sure that the incoming signal does not have more than the frequency I thought it would, right? If I'm sampling at, let's say, 100 kilohertz, then I need to make sure that the signal didn't have frequency more than 50 kilohertz. So usually that's the job of analog circuits. They kind of filter things away. It's something called anti-aliasing filter. So there's usually this analog circuitry sitting around in a lot of embedded processors. Do have this kind of circuitry built in order to do so. Okay. So, and finally, actually, another thing I wanted to point out is sometimes I can use digital pins as a way to generate analog signals. And let me explain how that's kind of a poor man's approach. So that's something called pulse width modulation. And you would find this thing very commonly in control of things like motors on a drone, for example, or a race vehicle or things like that, where you are trying to send an analog value to the rotor or to a wheel, telling it what speed to run at or what position to go to. So one way I could do it is to generate an analog signal, right? I can generate an analog signal with the right values. I can say 5 volt means full speed, 2.5 volt means half the speed, and 0 means stop. I could do that. But alternatively, we can convey this information with a single wire digitally. And I'm sure many of you have seen these things, where kind of the idea is that I could change, I can send a periodic signal, and the duty cycle, that is the fraction of the time the signal is high, indicates the value. So I may send a signal at I'll pick some frequency for my base frequency in the hood. So I can basically say, maybe let's say this thing is one millisecond, let's say, for example, and then the fraction for which I'm high, the signal is high within it, indicates the value. So this is called pulse width. There is a counterpart called pulse position, in which case, again, I will have a period, and the pulse of a fixed width will come at a particular location, in which case the location indicates what the analog value is. So I can take, so in this case, I'm just generating zeros and ones, and I can generate these signals using a program very easily. And then the value is indicated by how many clock cycles I'm high versus low for, or where the pulse is located. So very commonly used where you want to avoid the complexity of having A to D converters and all, and you just want to have a good software control, to the extent that you would see that many processors have these things built in. In fact, if I were to kind of go back to where I had, I have to go back a lot, but let me just do that. Okay, here. If you notice, this processor has a PWM signal coming out directly. So that means it has some hardware in there to which I can simply tell what value I want to be output, and it generates a PWM signal with the desired waveform. I don't even have to do it in software other than to issue it. So lots of processors in these embedded systems provide pulse width modulation support for it, because it's just so useful. If any of you have worked with drones and all, you would know that the motors in the drones, same thing with race car, model race cars and all, they all operate off PWM, very common. So it's used for motor speed control. Now the question is how, right? I mean, thus far all I'm showing to you is the digital signal, what happens under the hood. So the idea is, of course, that the average value is indicating the actual true analog value, right? So the 25% is, if the pulse width is 25% of the max, is saying 25% of some maximum voltage, right? So, so for example, 90%, I guess in this case, the value is what? 12, so 12 volts. So depending upon, so 50% corresponds to a 6 volt average. So I want an average signal like that. How can I, so my motor under the hood needs an analog voltage, right? It needs the voltage of 6 volt when I send 50%. But I'm generating this kind of a square wave waveform. How do I get 6 volt from this digital signal? Any of
like a low pass filter?
Yeah, let's put a low pass filter. A cheap low pass filter will do the trick, and you're good to go. Okay, great. So now, oftentimes you don't even need an explicit low pass filter, because your system already has enough low pass filtering built in. So for motors specifically, and by the way, you'll find these things, you'll also find them in your LED lights. Actually, if you buy LED bulbs for home, they also use a very similar type of thing. That's why when you dim them, they operate this way. So what happens out here is, let's imagine I have a motor, and what I will have is, I'll put them into the structure which is called as an H bridge. And the idea is that I connect one end of the bridge and the other end of the bridge to some fixed voltage. So this might be 0 volt. This, in our case, this is 12 volt. And then our signal basically controls these switches. And kind of the idea is that the fraction of time the switch is on versus open, closed versus open, dictates the fraction of time the current is flowing through the motor. And then motor itself has enough inductance and capacitance to take care of low pass filtering. So this kind of an H-bridge structure where you're using some switches and usually some transistors does the trick very nicely. So you can do speed control, position control, intensity control, these kind of things very nicely. What's the gotcha? The gotcha is that we are to convey an analog value, I need significant amount of time, right? In the previous example, I used the value of 1 millisecond, which means that I am wasting a lot of clock cycles. My responsiveness is slower. So if I need rapidly changing analog values and all, I can't do it this way. But when you are dealing with things like light and motors and all, they operate at a much slower scale. Their dynamics are in millisecond range. Okay, so it's perfectly fine. So PWM work very well for this class of application. On the other hand, if you need more agile analog signal, then you should use a proper D2A converter. PWM signals are also used to convey information from sensors to the processor. So sensors to monitor motor speed, for example, they use something called quadrature encoding. Let's see, I may have some slides. No, I don't have them. What happens there is if you look up for quadrature encoder, you would find that PWM signals in those cases are being used to convey information from the physical world to the processor. Okay, so again, very commonly found built in the processors, quite possibly in this processor too. And if nothing else, there are good software libraries and all to let you deal with this. So you could convey information, analog information riding on top of a digital signal like this without needing an A to B converter. Okay, let's see. So how are we doing on time? We still have around 20 minutes. So okay, so other things when we are conveying information. So like you may have to send information over to a peripheral or to another device. Then additional considerations come into play. What data rate, what distance, do you need to go wireless or wired, how many wires you can carry, all these kind of issues come into play. So you would find on these chips a variety of specialized IO interfaces that exist so that you can talk to devices, and there is a whole ecosystem of devices you can buy which speak these standard interfaces. And in particular, on more common on microcontroller are the various serial interfaces. So you may have heard of these terms like I2C, SPI, UART, USB, USBM. Well, we all know, and there are a whole bunch of others. And then there are also parallel interfaces like PCI Express, for example, which I'm sure you have heard of. And then there are interfaces which are more specialized and for even longer distances. Ethernet, we all know, but CAN, which stands for Control Area Network, and it is used in cars. All cars, or well, all non-electric vehicle, all gasoline-powered cars in this country, for example, they have a CAN bus running which ties together all the computers inside the car, and then this bus is brought out onto a port which sits kind of underneath your steering wheel, for example. Importantly for us are the wireless ones, and there are a whole bunch of them. Now, the particular Arduino device that you have has BLE. It actually also has Zigbee, as I mentioned earlier, Zigbee 802.15.4. But there are others. You have some older thing called ANT, Wi-Fi Direct, which your phones have, Z-Wave, which is another standard which is used by a lot of products at home. If you smart home products, they tend to use it. Over a longer distance, there's something called LoRa, long range. It has become very common. It can give you miles of range, so they are being used quite heavily in city scale sensing. So, so you have wired stuff, which is intrinsically short range only or mid range only, and you have wireless stuff which can go truly long distance, like miles kind of distances, and of course short range stuff. So rich set of stuff exists, and really kind of an alphabet soup of different standards and all that exist and all. But commonly speaking, on your board, if you look at the GPIO and all, you'll find these things. So these are important. PCI and all, frankly, you need to move to next higher tier of systems. And CAN bus is in the automotive domain, although they have some new standards emerging there. And then for wireless, Bluetooth BLE is probably the most dominant one. And then Zigbee is probably the other one, which is of quite a bit of interest. And then at city scale, LoRa and its cousins have become extremely have become quite popular. Okay. When it comes to wired interfaces, you can have interfaces which are parallel, as in data goes over multiple bits, and then you may have a clock signal which is going over it, and versus serial, where bits go one after another on a single piece of wire, and usually accompanied by a clock or sometimes no clock. Okay. My question, if you have to send very high rate data, which one would you use? What do you think the trade-offs are?
If you go with the parallel interface, you have to worry about timing synchronization between the different lines, which can be a limitation. So you might be better off with multiple serial lines.
Yeah, exactly. And which is why you see that all our high-speed links, Thunderbolt and USB, high rate USB and all these kind of things, they're all single, they're all of this type. Okay. And so the reason precisely that you're bringing out, which is if I were to send these bits, even tiny differences in the length of the wires or mismatches in capacitance values and all, what may mean is at very high rate, I may be sending the bits out simultaneously, but they don't arrive simultaneously out here. So I may be sampling some bits of one symbol and some bits from the next symbol, for example. So that can create utter chaos. So high rate links tend to be, well, they are basically this. If you are doing parallel one, particularly if you're sending them over cables, it's pretty hard to get them right. If you have a PCB bus where you can very precisely control the layout and all, maybe you can do it. But otherwise, that's why you see like how fast is USB now. So I think the Thunderbolt 3, which is on the modern laptops and all, goes up to 40 gigabit per second. So very fast, right? I mean, if you think about it, you're really talking about now way into sub nanosecond regime. Okay, so and yet we go through. Let's see. I think I have a 40 gigabit Thunderbolt cable, and it's around a foot long. That's I think pretty much the maximum speed. If you want maximum length, if you want to go more, they actually have optical cables and all. But it's pretty amazing that we can do 40. I mean, not too long ago, USB meant 480 megabit per second. So we have come 10x there. So serial is the way to go. Now, so serial, as we just discussed, obviously is low pin count, avoids timing issues. But if you don't have a clock, then you may need to do recover the clock. So in this example, you were sending the clock separately. But if I don't set the clock, then I may have to make sure that from the timing of the bits, the receiver can figure out its clocks. So that's what happens in your typical serial port. And also kind of it's a more complicated software interface to deal with. One jargon that you would see is synchronous versus asynchronous, and that really means whether I'm only sending the data or am I also sending a clock. Another jargon is whether your link is full duplex or half duplex, as in can I communicate on both sides simultaneously, or can I only one party can send to the other at a given time. Master slave, who initiates the communication, right? So this is really about that one device is a master and others are slaves. Usually that's the case in most of these protocols, but sometimes you also have multi-master buses where multiple devices can initiate communication. So in which case, if multiple devices can initiate the communication, then you would they come with some sort of an arbitration scheme. So for example, CAN bus that I referred to earlier is an example of a multi-bus thing. I2C is also multi-bus, but SPI is not, for example. So they all exist on your chips, and one has to just consider them. Let's see. I think there's some more of these details. Most common are these: UART, I2C, SPI. Anyone knows the difference between UART and RS-232? I'm sure you have encountered both these terms for serial ports. So UART is the basic serial communication protocol, which is very common when you see bit rate on the modem and all. Okay, RS-232 is a specific voltage standard on top of it. So most of our devices that you get, they have UART, but they typically won't have RS-232. RS-232 is at 12 volts and all, so usually they don't have that. But when you have a proper serial port on a box, then it will be RS-232. But these little devices are just UARTs, and there is a way to send UART data over USB. So most of the things you encounter is really UART sent over USB. That is why, for example, your Arduino devices and all, they connect to your computer over USB. Okay, I2C and SPI. So almost every microcontroller will have a UART, even if it doesn't have the others. It's very, very common. In synchronous mode, you can go up to a couple of megabit per second. You can go up to a few 100 feet. But you do need to configure different sites so that they're using compliant protocols. So how many start bits are there? How many data bits are sent in one go? And are you sending any error checking parity bits or not? So very common, very routine hardware implementations and software implementations abound. So very common way of connecting things. And as I said, oftentimes now we send UART over USB. Okay, so don't think I need to spend much time on this. The main thing internally, the way it works is that by the start bit, there's no separate clock going out. So as I'm sure you must have seen in some undergrad course or other, the way the receiver works is that by looking at the start bit, you measure what the precise clock rate is. The challenge that we face is clocks on the two sides may not have exactly the same frequency. So basically, the start bit is used to both indicate the start and also kind of learn what the precise time period is, and then you sample at the middle of the bit and get the bits out, and then the parity bit basically provides you error correction. So very simple to do. You send one character at a time. As you can see, there's a fair bit of overhead to send 7 or 8 bits of a character. You need to send a start bit, you need to send a parity bit, and you may have some idle time in between. So I'm going to skip this. I2C, that's far more common for sensors because it allows a higher rate interface. It came from Philips, the European company, and the way the main thing is it allows for a very structured way to address devices as well as to have multiple masters. So you would see a lot of sensors on the boards and all. I wouldn't be surprised if the sensors in our little Arduino are also I2C based things. It's very common. Okay, and the way they work is that all the different devices, their output signals are all ended together into a single wire. Okay, so kind of the idea is that this wire out here, it's pulled up, and then individual devices, only one of them would be driving it at any given point in time. So essentially, this is how you get the ability to have multiple devices sharing the same bus. So in your digital logic courses at the undergrad level, you might have seen things like wired and interfaces. So that's what I2C implements. So it's an addressable communication protocol. A master can communicate with a specific slave. So each sensor, for example, or each peripheral would have an address. You can talk to it. You can go to fairly reasonable speeds, a few megabit per second. So very, very commonly used. Okay, I'm going to skip through this. The final interface you will encounter quite a bit for very simple stuff is SPI interface. And SPI interface is really, really super simple. There is a clock and there is uh, data lines for input and output respectively. And then there is a separate slave select signal. So kind of the idea is that you basically literally uh, toggle the clock, and then every clock tick you send a different bit. So very simple protocol, no addressing, nothing going on. So we just toggle the clock and make sure that the SO has the right bit. And on the SI side, you monitor the clock, and every tick you read in the SI. So you can do it very quickly in software, as well as many of these processors have hardware support for it. So SPI is very commonly encountered for talking with certain radios and memory chips and things like that. So again, you can achieve reasonable rates with these. So I2C, SPI, and UART are there. In SPI, you can have multiple slaves, but for each slave, you will need a separate select signal. Okay, so the number of pins grow up, whereas in I2C, there is an address. So you basically don't, number of pins don't expand as you add more peripherals. So SPI is super simple, but it does have disadvantages, foremost being that it uses more pins. It doesn't allow explicit addressing within the signal. Okay, there is also no flow control. Flow control refers to what if one master is sending the data and the slave is not able to read. So there is no stopping, like you can't say wait for the data. Whereas these flow control signals exist in other protocols. So there's a whole bunch of trade-offs that exist between these things. Again, I2C is probably the most sophisticated of the lot, and you would see a lot of peripherals using it. There are some other stuff that you might encounter, and then finally USB. That, of course, is the main one which we encounter in the bigger computers. Your little Arduino actually can act as both USB slave and USB master. So it's actually a pretty sophisticated USB that exists on that little device. So one can kind of use that. Okay, so let me see. Yeah, I don't think I can say anything about here. So the final one before I stop for the day is this control area network. And the reason I want to mention this is because if you want to do any project around involving your car, because very easy to interface and suck information from the car and all, you might have seen these gizmos you can buy which attach to the OBD2 port. On your car, so that's the CAN bus. But another interest is that it's an example of a multi-master bus with a particular arbitration protocol, which is interesting. So what happens in this is that inside the car, there are all these little computers essentially sitting on this network, and each one of them can transmit a packet at any time. So the engine, they want to send some information to the brake, or nav unit, they want to send something to the engine and whatnot. Okay, so the way the CAN bus works, it's a pretty old bus, as you can see, and the data rates are pretty low, and it's actually in the process of being replaced by a more modern bus now, which they are trying to standardize. But just wanted to give you an example of how it works. Okay, so I have a bunch of nodes. So let's say I have node A and B, and they may decide at any time they want to transmit. So what happens is that these nodes are given addresses which indicate their priority. So higher address may mean higher priority, for example. And what happens is that again, so each node has a transmitter and a receiver. So it transmits on the, when it chooses a transmit, it transmits on the transmit line, and then it also hears what is being sent. Now the transmit lines are all tied together, very much like they were in I2C. So, and when a node is not transmitting, it is not going to send anything on that line, as in it will not send any voltage. So it just keeps it open. So now what happens out here is that there is the way the arbitration works is that every clock tick, starting at some known clock tick, every node will send out its address. Okay, so so it is going to send the bits one by one on each clock tick, and every clock tick, the node will also monitor the bus and say, what I'm hearing on the bus, is it the same as what I transmitted? So for example, in this particular case, what you see out here is, let me see if I can get my pen back. Okay, so at every clock tick, after the start bit, so you see different bits being sent out. So on this clock tick, node A and B both sent a 1, and so they will hear back a 1. On the second clock tick, both of them sent a 0, so they will both read back a 0. On the third clock tick, both of them sent a 1, both will get back a 1. But on the fourth clock tick, the one with the gray, node A sent a 0, node B sent a 1. But because things are tied together in this wired ANDing manner, on the bus line, 0 overrides 1. So what will happen is node A will see that its readbacks a 0. Node B will also read back a 0, but node B will say, hey, I have a discrepancy. So node B will drop out. So one by one, every time a node sees a discrepancy, it basically stops participating in this arbitration. And at the end, because everyone has a unique priority, unique address, only one node will be standing, and then that will go ahead and transmit. So this is what is called as bitwise non-destructive arbitration, but it takes n cycles if you have n bits of address, or the address could be dynamic. So like the same node may send messages with different levels of priority. So you can think of this thing like a priority-based protocol, and the message with the highest priority is the one which kind of goes through. So that's how CAN bus operates. It's been there, I mean, if you notice on the previous slide, for a couple of decades. It started in 1980s, so it's been there. There are a lot of papers and all discussing kind of issues and all that arise because of this particular arbitration protocol. What do you think is the main, with this kind of arbitration, what do you think is the main problem?
It's possible that somebody with a low priority may never get their message to get sent.
So that's excellent. So this is a starvation problem. Low priority. So if there is a chatty high priority node, it will just basically always hog the bus. Okay. So it's not a fair protocol in some senses, and that goes on to show that why we need protocols or schedulers which take into account some better sense of who gets a chance to transmit. It's the same issue in computing also, right? If the operating system were to always give the CPU to the highest priority process, highest priority task that is ready, then the low priority task may be starved out. So the same thing which is going on out here. Okay, so I'm going to stop out here, and we are going to move to software organization next time around. Next week, I'm also going to spend some time as I talk about the software organization also in context of the board. So if you haven't ordered the board yet, please do, so that you have access to it next week. That would be terrific. I will still proceed with it, but it would be better if you are able to try things out and set yourself up. I'm going to put some documentation on the recommended software tools and all around it. I mean, it's pretty straightforward, but still I'll document it. But we'll discuss that next week.